Hello everyone, and welcome to the last part of section 3.6, where we will be going over damped force oscillations. This is where we're going to put together everything we've learned so far, using a system that has a damping constant and force. First, let's take a look at our general equation. As shown here, it is mx double prime plus cx prime plus kx is equal to f naught of cosine of omega t. In this equation, m represents the mass, c represents the damping constant, k represents the spring constant, f naught represents the force, and omega represents the angular frequency, and t represents the time. As we learned before in section 3.5 with the non-homogeneous solutions, our solution will be in the form x equals to xc of t plus xp of t. In the case of mechanical systems, xc also has a different name called the transient solution. As time goes on, the transient solution gradually approaches zero, which leaves us with only the particular solution, which we also call the steady periodic solution. Make sure you remember that xc is the same as xtr, and xp is the same as xsp. Now let's go over how to find x sub c of t, which is the complementary solution. So we went over this a lot in section 3.4, and just for review, we separate it into three different cases. If c squared is greater than 4km, we have x sub c of t is equal to c1 e to the r1t plus c2 e to the r2t. If c squared is equal to 4km, we have xc of t is equal to e1 k negative pt times c1 plus c2t. If c squared is less than 4km, then x sub c of t is equal to c1 e to the negative pt times a cosine of omega t plus b times sine of omega t. Remember that these three cases are called overdamped, critically damped, and underdamped. Make sure you memorize these equation forms. Next, let's go over how to find the particular solution xp of t. I'm going to derive the general form of x of p in this video, which should provide you with a formula that can instantly solve these problems, but it's also important to know the process. So I'll get started how we normally get started in finding a particular solution for a non-homogeneous equation. So when we look at the right side of our equation, it has f naught cosine of omega t. And this cosine term tells us that our general form for our solution is going to be in the form a cosine omega t plus b sine of omega t. Next, we can take the derivative of this equation, which is going to give us x prime of t is going to be equal to negative a omega sine of omega t plus b omega cosine of omega t. Let's do this one more time and take the derivative, which is going to give us x double prime of t is going to be equal to negative a omega squared cosine of omega t minus b omega squared sine omega t. Then we can do our usual process where we substitute in each of these as the variables highlighted in the original equation, and then set the cosine terms equal to f naught and the sine terms equal to 0. And this is going to give us k minus m omega squared a plus c omega b is equal to f naught, and then negative c omega a plus k minus m omega squared b is equal to 0. I skipped the part where we just combine the like terms and set up the equation, but you can do that yourself if you like. Next, we can solve this system of equations for a and b. So we're going to get a is equal to k minus m omega squared f naught over k minus omega squared plus c omega squared. And b is going to be equal to c omega f naught over k minus m omega squared plus c omega squared. Remember, you don't have to memorize these by any means, but I'm just using it as a way to show how we get to our final solution, using a general form. Now let's go back to our general solution for xp, which is the steady periodic solution. So we want to express this in a way such that it will only contain one cosine term, so that it's much easier to see how this oscillation is actually represented by a cosine curve. We can do this by bringing back the phase angle, which is something we talked about back in section 3.4, and essentially the phase angle is just the angle that is formed if you create a right triangle with side lengths a, b, and c. Because of this, we can replace a with c cosine alpha, and b with c sine alpha, which gives us the equation shown. We can further simplify this down using the angle addition formula for cosine, and that's going to give us xp of t is equal to c times cosine of omega t minus alpha. And now we're basically done. This is pretty much as simplified as we can make the expression for x of p. So now we'll just find what c is and what alpha is. Because of the right triangle I talked about earlier, c can just be represented as the square root of a squared plus b squared because of the Pythagorean theorem. And when we plug in the values for a and b, we're going to get that c is equal to f naught over the square root of k minus m omega squared plus c omega squared. We can also easily find what tangent of alpha is, as it's just opposite over adjacent, which is b over a. When we plug in b and a, this is going to give us c omega over k minus m omega squared. If you go back and take a look at the equation that we derived for b, you'll notice that the numerator and the denominator are both positive, meaning that b has to be positive, and same applies to c. So this means that sine of alpha, which is b over c, is always going to be greater than 0, which means that alpha has to be either in the first quadrant or the second quadrant. Because of that, we have to be careful when we take the inverse tangent on both sides to find alpha, because our solution for alpha has to be within 0 to pi. Keeping this in mind, we're going to have 3 different cases on what alpha is going to be. If k is greater than m omega squared, it means the expression tangent alpha is going to be positive, so we can just straight up take the inverse tangent on both sides. However, if it's smaller than that, alpha is going to be negative, so we can just add a pi to bring it into the first and second quadrant. Finally, if k is equal to m omega squared, then the bottom is going to become 0 and tangent's going to be undefined, and this means that it's right at the point where alpha is pi over 2. Now that we found both xc and xp, we can plug it back into our overall solution, which is going to be the sum of them. There are a bunch of forms for xc, so I won't write them all out, but we can substitute in our xp, which is going to give us the general solution, x equals to xc of t plus c cosine of omega t minus alpha. Make sure you write this down along with the formulas for c and alpha. Lastly, we're going to go over something called practical resonance, which is the global maximum when c is graphed as a function of omega. Remember that c can be expressed as f naught over the square root of k minus m omega squared plus c omega squared. Here's an example of what happens if you graph omega against c. That point at the top there is the point of practical resonance, and can be found by taking the derivative of the function and setting it equal to 0. And that is going to be it for this lesson, and I'll go through an example in the next part. Thank you for watching.